Hello, my name is Chao, and I'm from Purdue University. And this is a work, this is a joint work with Qiming Huang, another PhD student at Purdue Stat Department, and also my advisor, Michael Zhu. And so our work, the title for our work is Optimal Kernel Group Transformation for Exploratory regression analysis and graphics. And basically, the problem we want to solve is how to efficiently and effectively explore the relationship between response and the predictor variables. And there are quite a few methods. And so first, the easiest way is we just focus on some features we're interested in. For example, in the ordinary least square or a linear regression, we just focus on the mean or expectation. And sometimes we're interested in the quantiles, so we use a quantile regression. And the second way, which is also popular, is we just estimate the conditional distribution directly using some non-parametric methods. So, but those two methods have some limitations, and the first one is obvious because we only focus on some features, so we can't really capture most or all of the information from the distribution. And the second one is usually we use non-parametric methods. So if you are estimating for high-dimensional data, and you will have some problem because, for example, if you use a spline, you have to construct high-dimensional bases, and once that dimension is high, the number of bases would explode. So that's the motivation. And the third method we found was very interesting is we first transform the variables before we analyze the data. So some well-known examples are box-Cox transformation, and we also found that the method ACE, which stands for alternate conditional estimation, is very effective in revealing the relationship between y and x. And the idea for ACE is when you are running regression, you transform each variable by using some non-parametric functions. And in the original work by Leo Breiman and his collaborators, they just estimate these functions from L2 space. And they just restrict, they use additive structures, but at the same time, they restrict to univariate transformations. So the advantage is the transformation is actually a feature selection procedure. So automatically, you are selecting what is the most important information from each variable, which can be contributed to the relationship between those variables. And also, since it's essentially just a regression techniques, so it's the computation would be very efficient. But the limitation here is that we only focus on the univariate transformations. So sometimes we have interacting behaviors between different variables. So this brought us the idea of generalizing or extending the existing method to incorporating group informations in the non-parametric regression. So instead of just doing univariate transformations, we can also do transformations for a group of variables at the same time. But also at the same time, we focus on additive structures. We like additive structures because it's simple, and when you are doing regression, the result would be easier to interpret. So the formulation of the grouped version of optimal transformation is given by this formula. And basically, you just want to minimize the mean squared error after you transform the variables. And so here, the original form, we have a G in the L2 space and F also in the L2 space. And this is a more general framework than the previous work. And when here, D denotes the number of transformations for predictors. And G is the transformation, P is the number of variables. And if number of groups is the same as the number of variables, this is the old univariate transformation framework. And if the number of group is just 1, so we just transform all the variables by one function. So this is just the maximal correlation. Okay, so so we want to estimate those functions, and so we want to find a good space which has some nice properties, so that it can help us to estimate the functions easily. So we choose kernel spaces because it has a well-known nice properties, and we can have reproducing properties and representers theorems. And then later on, we will use them for estimating our functions. Also, another good property for kernel spaces is that since we are transforming a group of variables at the same time, we are dealing with high-dimensional functions. So kernel can easily accommodate high-dimensional structures. And also, in this space, we can formulate our grouped transformation as the eigenproblem. And the sample estimators only relies on the graph matrices. And the proof of consistency would be also simple. And we coin this framework as optimal kernel group transformation. So the setup for our OKGT is that for each variable or each group of variables, we equip it with a separate kernel function and the corresponding RKHS. So basically, you can have a separate spaces for each variable or each group. But in our application, we just restrict it to the same kernel functions, so all of them are the same. And then the formulation, the mathematical formulation is the same, and except that now we restrict our search space to be the RKHS instead of the L2 space. And later on, we will show that as long as you pick a proper kernel function, then the estimate would be consistent in the L2 space. And also, because we use additive structure, so we are dealing with this additive RKHS and for our estimation. Okay, so so we want to extend the univariate transformation, and by incorporating the group structures, and we also use the kernel space. And then the third tool we use is we use the covariance operators to facilitate our analysis. And so here, this is just the definitions for the cross-covariance operator and the covariance operators. So basically, the cross-covariance operator is just the covariance matrix in the functional domain space. Okay. And also, we rely on this conditional covariance operators, which are defined in terms of covariance and cross-covariance operators. Okay, so since we have a additive space for x and RKHS for y, and we can easily define our covariance, cross-covariance, and the conditional covariance operators in those corresponding spaces. And a remark is because of the additive structure and the covariance operators for x, RXX has a matrix representation. So basically, each component is a covariance operators for a individual RKHS. So how does this covariance operator thing related to our group transformation framework? So this is the key proposition connecting two things. And this is due to Fukumizu and Buck and Michael Jordan, 2009 paper. And basically, if you use the conditional covariance operator of y given x, and y and x, and apply that on G, then it recovers the minimum mean squared error in the y space. Okay. So basically, this is just a functional version of regression. So now our original formulation of the optimal kernel transformation is just can be reformulated by using this conditional covariance operator. And originally, we want to do this minimization problem, and it's equivalent to this maximization problem. And this looks like some eigenproblem, but not exactly, because the constraint is not the norm equals 1. So then we just do a little trick, and we define this phi to be RYY square root of this covariance operator times G. Then the constraint becomes the norm 1. So this becomes exactly a eigenproblem in the kernel space. And then the optimal transformation is just you find the largest eigen vectors for this matrix, and then project it into Y space. Then you find G, and you just project G back into X space. You find the F. Okay. And then the largest eigenvalue is we denote it as a R squared. Basically, this is it has the same meaning as the classical R squared in the linear regression literature. Okay, now the estimation. So because we use kernel space, so everything can be represented as a gram matrix. So we use the gram matrices to estimate each covariance or cross-covariance operators. And because we use additive structure, so the covariance operators of X is just the block stacks of those individual gram matrices. And here, in order to enforce the zero mean constraints, we just use centered gram matrices. And then, so this VV is just this long, horrible matrix in the previous slide. So in the estimation, we added a regularization term because even though for some kernel, we can, in theory, they are invertible. The matrix is invertible, and in practice, we cannot guarantee this. So we added a regularization term to make sure that it's invertible. So now the sample version of OKGT is given in this box, and you just need to perform eigendecomposition so to get the largest eigenvalue and the eigenvector. The eigenvalue is the empirical R squared, and this alpha is the expansion loading for the functions in the kernel space. And then G and F is just similar to the previous population version. Okay, so in this work, and we also focus on graph structures. So we have to address this problem. So currently, we propose a random partition. So basically, if you don't have any group information for your predictor variables, we just perform a random partition. And we wanted to keep each group of variables to be to have a low size, so that later on we can use graphical tools to visualize that. And but also currently we're working on how to optimally detecting the group structures. And this is just some theory behind this method, and it has two parts. So the theorem 1 and the theorem 2 just shows the estimator in the RKHS is consistent in the L2 space as long as you are using a kernel which is dense, which has a RKHS which is dense in L2. And the idea for the proof is just based on the covariance operators. So we just prove that the covariance operators is consistent in the space. So this is just a simulation work, and so the model is simple. So each one has its own transformation in the true model, and we can effectively recover the original functions. And here we can successfully differentiate the absolute transformation and the quadratic transformation. And we used both Gaussian and Laplace, and it turns out that the Laplace performs better, so that's why we reported the Laplace result. And this is because we have a group structure here, so we also can also recover the group structure successfully. And then we also try to understand how the group structure can affect the result. So we tried different, for this true model, we tried different group structure settings. And the first one is the most general one. So we just transform all the variables by one function. And number 6 is the most restricted one. We just do univariate transformations. And so this is the result. Basically, we just run each setting 100 times and report the box plot for the R squared. And number 5 is the true model, true structure, so it's the best. But it turns out that number 3 also works similarly to the true model in terms of the R squared. So in this case, this means that in practice, we don't really need to find exactly what the true structure is. We can use a, say, approximation structure, and it can still perform very well. And then we also tried two practical, two real data. And the first one is gaming data. Basically, the response is the professional level for each player, and the predictor is the measure for each type of skills for the players. And so after doing we use 3 settings. And the first one is we have a group size 15. So basically, each one is univariate transformation. And the D1 is the most general one. And number 3 is we transform each group of skills. So because in this data set, we have some information about the grouping. So this is the result for univariate transformation, but it's still very it's still interesting. So because you can see that by transformation, after transformation, you can see the improvement of skills is not linear. And at the lower professionalism and the higher professionalism, the increasing of your skills is much higher than at the other levels. And also, we tried the medical data, which is the TCGA glioblastoma multiform data. And the response is the survival time for each patient, and the predictor is the number of genes we have. And because here we have a very large number of variables, so we first did a screening. And we selected the top 13 genes based on the maximal correlation between each gene and the survival time. And we do this transformation. And it's clearly that the relationship between the genes and the survival time is nonlinear. And it seems that there is something interesting happening at 2 for each gene. This is the expression level for each gene. But if you really want to find what causes this nonlinearity, we need a further investigation. And we also run different group settings for this data set. And it turns out that the number of groups equals 10, what gives us the highest average R squared. So which means probably we have a bivariate interaction between genes. But what's the interaction? We need more information for that. Okay, so just a summary. So in this work, we're just achieving some goals to extend the ACE to incorporate the group information. And we also use the kernel space to facilitate analysis and estimation. And we also use covariance and cross-covariance, conditional covariance operators to study the dependencies between variables. And some future works. And we understand that we need an optimal procedure to detect the intrinsic group structures. And we also know that you need a good way to select a optimal kernel functions. And we also need more general tools to visualize our results. And we also need, I'm also working on imposing sparsities on those predictor variables so that maybe some variables is not really necessary in our regression setting. Okay. This is our work. Thank you. How did we find the groups? So one way is you have some previous information, prior information. So like the gaming data, you have different skill groups. So you do the corresponding transformations. And also currently we just propose random partition. And currently we are also working on optimal way to select the group structures. Like currently I'm experimenting stepwisely adding variables into our regression setting, and also yesterday I was at the poster session, and someone proposed maybe I can use the graphical lasso to impose some penalty so that I can have some diagonal structures in my covariance matrix structure.